So we've had a lesson, or the lesson previously was discussing Ohm's law. So this is resistors in series. Now we'll go through these. These are quite basic little calculations, but we will use these when you come on to testing, when you come on to doing design projects, when you come on to doing various things. This is one of the fundamental building blocks for the electrical. So basically with resistors, you just add them up. R1 plus R2 plus R3 equals the total resistance, RT. Now, you may find on some slides it might say RS or some things like that, but it's the total resistance. So basically, you're adding them up, and you'll see that if we go on to some testing later, is quite a fundamental side of things. So to calculate the total resistance of a circuit, we add them up. So in this case, we've got 2 plus 5 plus 8 plus 3. So it gives us 18. I'm trusting that the Sitting Gills PowerPoint presentation I've got has got that correct, working that out in my head. But you just add them up. So that then gives us the total resistance of the circuit. So to calculate the current flowing through the circuit, first of all, we would need to work out the total resistance of the circuit. So first of all, even though this calculation actually doesn't look quite right to me, so we've got 2 plus 3 plus 7, which gives us 12 ohms. So it gives us 12 ohms, and with a voltage of 24. So if we were to do our ohms triangle, so this calculation at the bottom gives us 12A. What it should say is 12 ohms. So it gives us 12 ohms. And if we put this into our Ohm's law triangle, now we have a total. We have 24 volts divided by 12, which gives us 2 amps flowing. So there are 2 amps flowing. So this is a different example. So when a potential is produced across a resistor of 23 ohms and the current of 10 amps is flowing through it, so we have to do 10 times 23 to gives us the 230 volts. So I'm going to just trying to look at this PowerPoint just to see if it matches what we were doing here. Yeah. So what we have here is a little bit more complicated, which is called Kirchhoff's law. And it's an algebraic sum of the voltages around a circle equal to 0, or the supply voltage. So what we'll do in a second here is we'll work out, so if we have a voltage across each resistor, so we have a voltage across R1, R2, R3, which will give us a voltage across each resistor. All those voltages added together will equal the supply voltage. So I'm going to go through an example with you now, and it will make more sense in this example. So what we have here is a circuit with 3 resistors, 3 ohms, 5 ohms, and 7 ohms. And we have a total voltage, a VS or a VT, a VS or VT, of 90 volts. So what we have to do, the first thing that we have to do is we have to work out the current flowing through the circuit. Now we have the one current. So the first thing we do is we add up all of the resistors. 3 plus 5 plus 7 gives us 15 ohms. Now we put that into our Ohm's law calculation. And with our Ohm's law calculation, we have 90 volts divided by 15, which gives us 6 amps. Now we have 6 amps flowing through this circuit. So if I just put the pointer on, so 6 amps flow through this circuit. So 6 amps flow through this resistor, 6 amps flow through this resistor, and 6 amps flow through this resistor. So we can work out, using Ohm's law, the voltage across each one of those resistors. So what we can do is we can have 6 amps times our 3 ohms, which gives us 18 volts. we have our 6 amps times our 5 ohm resistor, gives us 30, and we have our 6 times our 7 ohm resistor, which gives us 42 volts. So basically all we've done is we've worked out the voltage across each one of those resistors, V1, V2, V3. And what they're saying with Kirchhoff's law is, now if we add those all back up, 18, 30 and 42, we end up with 90 volts, which, as we can see, is what our original supply voltage is. So Kirchhoff's law is a way of checking to make sure that you've done all the calculations correct. And it's called Kirchhoff's law, and then we've just proven Kirchhoff's law. So I'm just going to come out of here, come over here, stop that.